Today I want to spend some time solving systems of equation word problems. Some of these can get pretty nasty. These are some of the uglier ones that we're going to see in class. So let's go ahead and dig in and see what happens. So here we have Pamela. She's requiring 3 hours to swim 15 miles downstream on the Illinois River. The return trip upstream takes 5 hours. We want to know Pamela's average speed in still water and how fast the current is. So before we get started, we need to dig back into our science class a little bit and come up with a relationship between the distance that we travel, the rate that we travel it at, and the amount of time that it takes. And if we remember, we have the equation that distance, the amount of distance that we can go, is equal to the rate at which we can go multiplied by the time that it takes. Or distance is going to equal rate times time. And hopefully that's a little reminder from science class. If not, now you know. So this works even if you think about a car. If we know that we can go 10 miles an hour and we're going for 3 hours, well, how far will we go in 3 hours if we go 10 miles an hour? You multiply your 10 miles an hour to 3 hours, that gets you 30, so we go a distance of 30 miles. And vice versa, if we know that we can go 30 miles, or we've gone 30 miles, and we've gone in 3 hours, we can find our rate. So 30 miles would equal our rate times 3 hours, divide by your 3, so we get 10 miles an hour. So in this case, we have Pamela going downstream. If we go downstream, if we think about going downstream, there's my nice going downstream, my rate is going to be what I can swim at, plus the rate of the current, because we have the water that's going to actually push us down the river as well. So we have two rates that are happening, our swim rate and the rate of the water. And this is going downriver. Likewise, if I'm going upriver, I have my swimming rate, but now that current is going to be working against me. So I'm going to take my swim rate and I'm going to be actually a little slower by what that rate of the current is. And again, we're assuming that our rates are going to be constant going up and down that river. So one thing to continually make sure of is that you look at this rate at which we're swimming and we're being added to if we're going down, up, we're going to subtract off. And now we can go set up our two equations. So my distance, I know I'm going 15 miles downstream and I'm returning upstream that same 15 miles. So I can go ahead and set up my downstream equation. So I have 15 miles is going to equal my rate. We've talked about this. I have my swim rate plus my rate of the current. So I'm going to let my swimmer be x and my current of the water be y. So here I have x plus y. And it took me 3 hours to complete that trip. So I know that 15 is going to equal x plus y times 3. Upstream, my equation, again, we're going 15 miles an hour. In this case, we have our swimming rate minus the rate of the current. So we have x, and there's our y. So now we have x minus y. And this time it took us 5 hours, which makes sense. It should take us longer to go upstream than it is to go downstream because we have that current working for and against us. Now we have a system of equations, two variables, two equations. What I like to do with this is go ahead and divide my 3 over to get x and y kind of by themselves. So I know that 5 is going to equal x plus y. And in my second equation, I know that 3 is going to equal x minus y. Through elimination, I can cancel out my y's. So I have 8 equals 2x, or x is going to equal 4. Remember, x is the speed of the swimmer. So we know that Pamela's average speed in still water, so if there was no current at all, she could go about 4 miles an hour. The current is our y value, so we can take and plug in our 4 for our x into one of our equations. I'm going to go ahead and do my top equation. So 5 is going to equal 4 plus y, so 1 is going to equal y. So we know that Pamela can swim at a rate of approximately 4 miles per hour in still water, and the current is approximately 1 mile per hour. And that's our first type of system of equations that we're going to be running into today. The next one, kind of my favorite, I don't know why. Again, a little bit of science here. And we're going to be mixing some solutions. So in here we have a mechanic. We have 300 grams of battery acid solution, and it has 60% acid in it. We want to add some water into this to dilute it so that we only have a 45% acid. And we want to know how much water we need to be adding. So whenever I mix chemicals, I always go back to my science class, and I think of two beakers. I know these are not going to be very nice looking beakers, but we're going to call them beakers anyway. And we're going to take our first solution. So we know that we have 300 grams. And I know that I have 60% acid of that 300 grams. So if I take 60%, or my decimal 0.6, times 300, this tells me how much acid I have. So I'm going to go ahead and label this as acid, and this as total amount. And we can think of it as total amount of solution if you wish. Right. To that, we're going to add something. Well, what are we adding? We're adding water. How much water are we adding? We don't know. That's what we're asking ourselves. How much water should we add? So we're going to go ahead and let that be X. Now we have to think about how much acid is in water. And hopefully, if you're drinking this water, you don't want any acid in it. So we should see that we have 0% acid in that. So we're going to take 0 times that X to tell us how much acid we have in that water. And that's going to equal our new solution. Well, how much solution do we have? We don't know. So that's going to be Y. But we want it to be 45% acidic. So we want 45% of Y to be our acid. So now we have kind of two equations. We have our top, which is our total amount of solution that we have, and we have the amount of acid that we have in our solution. So I can go ahead and write my two equations. 300 plus X is going to equal Y. Again, X is the amount of water that we're adding, and Y is the amount of solution that we're going to have at the end. So we're going to say end solution. And our second equation is the amount of acid that we have. Well, we have 60% of 300. 60% of 300 is 180, plus 0% of X, which is going to be 0x, is going to equal 45% of our Y solution, of our total end solution. Now again, we have two variables, two equations. On this, we have already eliminated our X's, so we know that 180 is going to equal 0.45Y, isn't it? Well, in that case, we can go ahead and divide by 0.45 if you wish. And we're going to throw that into the calculator because I don't expect you to know how to do that without a calculator. So if I take and divide that out, we end up with 400 equals Y. So we know that our end solution is going to have 400 grams. Well, if that's 400 grams, we know that's up here. We also know that that's up here. So we know that 300 plus X is going to equal 400. Again, that comes from our first equation, substituting our Y for 400. So we can go ahead and solve for X, subtract to 300, so X is going to equal 100. So we know X is the amount of water that we're adding, so to answer the question, we need to add 100 grams of water in order to dilute this 300 grams of 60% solution down to 45% solution. So to answer the question, we're going to add 100 grams of water to the 300 grams of acid solution. All right, and we have one more. This is kind of I enjoy the chemistry ones there. But we have one more, and this is going to be a money problem. So we're going to the bank. We love money, money, money. We're going to give you, or they're going to give us $1.50 in change, and they're going to consist of nickels and dimes. If we know that we have 22 coins in all, how many of each type of coin do we receive? So again, we're looking for each type of coin. So we have nickels and we have dimes. To make it a little easier, we're going to go ahead and label our X as nickels and dimes as Y. And what do I know? Well, I know that we have 22 coins in all. So I know that the X and the Y's have to add up to be 22. I also know their face value. I know a nickel is worth 5 cents and a dime is worth 10 cents. So I know that 0.05 X's plus 1/10 Y is going to equal $1.50. And there are again my two equations with my two variables. So I can go ahead and solve for X and for Y. Well, if we notice that second equation, I have a lot of decimals in it. We could go ahead and clear those decimals if we were to multiply that equation by 100. And you may wish to do that. If you don't want to work with the decimals, you're more than welcome to work with decimals. Myself, I would prefer to get rid of them. So if I multiply my 100 in there, we get 5x plus 10y is going to equal 150. Now I've got a nice equation I can work with. If I go ahead and actually, if I look at this equation, I can divide by 5, can't I? So coming down here, we have x plus y is going to equal 22. If I were to divide each of these by 5, I get x plus 2y is going to equal 30. And that actually becomes a little easier problem, doesn't it? So now, if I multiply my top equation by a negative, that's going to eliminate my x's. So I get negative x minus y equals a negative 22, and x plus 2y is going to equal 30. Adding these two equations together, my x's cancel, so I get y equal to 8. So I know that there are going to be 8 dimes. And then how many nickels do I have? Well, I know that x plus y has to equal 22. So I know that x plus 8 has to equal 22. So x is going to equal 14. So I know that there are 14 nickels. And you could go ahead and figure that value out. If we have 14 nickels and 8 dimes, 14 nickels is worth 70 cents. 8 dimes is worth 80 cents. So 70 plus 80 cents gives us $1.50. And those are going to be 3 examples of the word problems that you're going to see. A little more complicated than we've seen in Algebra 1, which is why we're calling this Algebra 2. Good luck and enjoy.